Current project due. Looks like it's already due. Let's see here. Today's the 3rd. Well, that's a good question. I guess. What about Saturday night? Sunday night? Mm-hmm.
Sunday night, first class is due.
And that'd give a week for the second pass, which should be enough.
Are we skipping the Python?
Yep, so the second pass will be the end of it.
There's no final exam, right?
There's, well, there is a final exam. The way it's worked traditionally, I'm sorry, I'm incapable of clicking and talking at the same time. Let me.
I know you talked about this too, so maybe
Yeah, no, that's fine. It's fine to talk about it again. The way I've done it traditionally is I break the class into groups of 3 students apiece, and each group comes up with 2 questions. They can be anything under the sun that's within a stone's throw of the kinds of things that we've been doing in class. And then I go and I look at both questions and I choose one of the 2 that seems most appropriate, and I'll correct it or beef it up or water it down if I don't think it's quite right as written. And then the final exam is taken by everyone in their groups again, and you're given a tar ball, which is in essence all those questions, and you work as a group to answer all of the questions. So in a 30-person class, there would be 10 questions, and I think when there are that many questions, I say like 8 of the 10 or something you have to answer. And you get a point, let me see, you're obviously scored, your team is scored on your answers. You get a bonus point for every point that other teams lost on your question. And there's a penalty if your question's so easy that everyone gets it 100% correct. Like a 5% penalty or something like that.
Are we talking like what is tell G, or more like write a program that does X and Y?
It can be anything. Probably what is tell G is not the best question because everyone will get that right, and you would.
I meant like the flavor of, you know.
There's some code posers where there's complex interactions of constructors and you have to figure it out. Some of them are essay answers about presenting they'll present some sort of OO design and you have to debate the merits of it. Some are to come up with a design. I think the ones that tend to be the best are the ones that require some sort of coding. Now, all that said, there's fewer than a dozen people in this class, which isn't enough to comprise an exam. So I think what I was going to do was choose questions from an exam. I don't know whether I'll go across multiple semesters or not. I'll spend a little bit of time poking around, but I'll find a set of questions that kind of the best of, the greatest hits kind of thing, and we'll have you assemble into groups of 3, and you'll have to go away with those questions. So it'll have to be scored differently since you can't get bonus or penalized, so it'll just be a straight graded type thing.
Is this class normally this small, or do you normally have?
No, I think I had fewer than 20 last year, but in previous years it's always been packed with at least 30 people in it. So I actually prefer it this way. I prefer the intimacy of the smaller class, definitely.
And then, is this how you do most of your other classes too for the tests?
No, this class is unique for this exam. Yeah.
Well, the idea of having a competitive test, so to speak. What if we don't do the group? What if we do it individually and everybody submits 2 questions from each person?
No, I don't want to do that. No, I prefer the teamwork on it, particularly since it's kind of open-ended and I didn't design the questions and so forth. It's nice to have multiple heads looking at it. Normally the strategy taken is, why don't you do questions 1 through 3, I'll do 4 through 6, and you do the remainder, and then you kind of check each other's work and you help each other out when you have problems. And so that's fine as well. You don't have to all 3 sit down and spend an equal amount of time on the first one and an equal amount of time on the second. You can divvy up the work, and then I would just counsel that you go over the answers together before submitting them. And submitting your answers is just simply creating a new tarball. It creates a tarball of a directory for each question, and you're supposed to answer the question within each directory, and then you bundle it all back up and submit it through Blackboard. So that's that. Tell me about what you've been doing the last 48 hours. You got any work that generates any questions? I have a little bit I can talk about, but I certainly don't have enough to fill a period. But I'd like to start with answering your questions if you have them. All right, then I will. Yeah, go ahead.
So I noticed that you have a first pass solution on the night.
Yeah, is that what we just said? Yeah.
Is that the object oriented?
That's the first pass. The object oriented will come the following week.
Oh, okay. Okay.
And I don't remember without looking, but there's something like 18 tests, and you have to pass the first 9 for your first pass solution, and then all 18 for the second pass solution, something like that.
I just refreshed the page.
Oh.
The link was available.
Oh, I see.
Yeah.
Okay. All right. Let's see. Let me demonstrate. All right, so what I was going to talk a little bit about is an issue that comes up. Let's look at the list of tests. All right. So tests 10 through 12 here. What is that? File 4, 5, and 6. So this is so there's your file, and you have your get stream position and your put stream position. You'll get that, you'll put it back, you get the I, and now your state, if you will, changes because you possibly are going to be matching ISSIP. So you read in the I, the S, you read in that S, you read in that, you read in that last S, and that last S was right, it was a mismatch right there. It was looking for a P, and you read in an S. So let's see, we would have read in the M, put out the M. Here we have a changed state because we have a potential match, and you read, boom, you read in that S. So here's the next character to be read in, and you have a mismatch. So what do you need to do? You have to put back all the characters that were mismatched. So these characters here. Yeah.
But you can't rewind the get pointer.
That's correct. You can't rewind, so you can't go back and reread them. The put pointer hasn't. So yes, that's a good observation. The put pointer hasn't moved, and the put pointer shows this stuff here. But keep in mind, if your search and replace are different sizes, and you get a ways into this thing, your put pointer is not necessarily going to be aligned with that, right? There may be a whole bunch of stuff. This stuff could all be in the deck, or it wouldn't be in the deck. You do, if you follow the one thing we talked about, you're only putting them in the deck if the put pointer is about to overrun the get, which is not true in this case. But there could have been previous stuff that happened beforehand that means this put pointer could be virtually anywhere, not necessarily at that point with the I in the file. So here's the question. Where else in your application, you've read an I, an S, an S, and an I. Somewhere in your application, even before you open the file, you have an I, an S, an S, and an I already stored that you could refer to. The search string itself has the characters that you were reading in, yes? Okay, so this gets to the memory minimization. You can't create a whole nother chunk of memory to store this stuff. So what you need to do is have some sort of concept of when you have a mismatch that you have a count of how many you've read in and ended up with an unsuccessful search. In this case, there would have been 4 read in unsuccessfully. So the next 4 characters have to come from the search string. Because you have to do a P, or you have to put out those that didn't match. Now it's a little more complex than that, but I'll add to the complex as if it wasn't complex enough. I'll make it even worse in a minute, but just running with me. You need to read 5 successfully. You've read 1, 2, 3, 4 successfully, and then your 5th didn't work. Now, talking about that 5th one for a moment, remember that I said we didn't have a queue, that we have a deck, and the reason was that you were permitted to push back one character. So if you wanted to, this mismatch character, this first S here, you could push that to the front of the deck so that once you start reading from the deck again, that would be the first character to come. Okay, so that eases that problem with this character that didn't match. But we still have these four here. So you know that you've read in 4 and your match was unsuccessful, so now you're in a state where you are basically getting 4 characters from the search string and spitting them out. At the beginning.
But it's ISSI is in the middle of the substring. It's not.
No, it's at the beginning. Here's right here. That's the beginning. This is the search string, ISSIP.
Oh, I was looking at Mississippi.
Oh, yeah, I'm sorry. This would be the contents of the file. Yes.
I think I've identified a possible problem with this. As we are loop searching for ISSIP, we've rented the I, the S, and the I, so that's four matches. Then we read the P, we get an S. But the thing is that this I and S are the start of the actual ISSIP, so we need to have a way of, like, we have a potential match state, read that potential match state, and maybe if we have a potential match and we reach another substring which looks like the start of the search, we have 2 potential match states, probably. 2 potential match states.
Right. So our mismatch overlaps our true match. So this is where I said, make it even more complex. So it isn't as simple as simply saying we had a bad read of 4 characters. Let's just put 4 puts out there coming from the search string. Because part of that, the very end there, that I specifically, ends up being what becomes a valid match. So you don't blindly put out characters from the search string on a failed search. What you have to do is start making that part of your search now. So let me give you a hint as to how you can survive this, and that is you have a state. Your state determines where you're getting characters from for trying to find a match. So you have a state which is I'm looking for a match. What we've been assuming now is I'm looking for a match is going to ask our buffered file, and then our buffered file will either get it from the deck or it'll get it from the file, right? Okay, so instead of always asking the buffered file for the next character, we have to check our search state, and we either get it from buffered file or we get it from the search string.
We get it from that.
And we're getting it from the search string for those remaining 3 characters. So let me take a step back. Let's rewind this all the way to the beginning. I do an ISSI, and then I have an S which is a mismatch. I am 100% certain that that first character of the search string, the I, is my mismatch, right? Let's simplify it. If our search string is, I don't know, S, and our replacement is Q. If I read, now I open up Mississippi Delta and I read the first character, I read the M. Is the M and a lowercase s? The answer is no. You're 100% certain that that M is not valid, so you just need to put it back out, yes? All right. Take that exact same verbiage here. If I read in, if I want to match ISSIP, regardless of how far along I read, as soon as I come up with a mismatch, I'm 100% guaranteed that that first character can be written out. That I is not going to be a valid match to anything. It's not going to be the beginning of a valid match to anything, right?
Otherwise, it would have been a valid match. Would have been
Yeah, the alternative is it is a valid match. If it isn't a valid match, then that first character cannot be part of a valid match. So on a failed search, the first thing you got to do is write out that first character. And everything else, now we have to see if the remainder of these four become part of a valid match.
What if we are looking at the searching and the replace string, and if we inside our as we have ISSIP and the searching underneath we have ISSIS. Well, if we I don't know how to explain, but I just had this idea. At the 0th character, and we detect the I as the start of a possible match, and then at the 3rd character, we also detect the I. So that's also the start of a possible match. So what if we maintain a possible match state for each possible match that we find? If we maintain a possible match a state.
You've got. I think you need to. You need to keep it as simple as possible. You have a state for what you're doing. Are you searching? Do you have a potential match? Do you have a successful match, which means you're going into a replace state? Or do you have a failed match? I think that's 4. Right, potential match, which is you're in progress for a multi-character search string. And you have either a success or a failed match state, depending on how that turns out. There's a separate state, which is where is your next character coming from? Is it coming from the buffered file? Now keep in mind, the buffered file, we've already got a nice abstraction there that's abstracting out a couple things, which means that the buffered file is clever enough to know whether the next character comes from the deck or comes from the file, right? So now we've got that encapsulated, nice little bit of OO there. We'd never have to worry about that again. Just to repeat it, that deck gets filled whenever we want to do a put, and these pointers are the put's gonna collide over the get. The put will always do a check, and if it looks like it's going to collide, then what you do is you do a get, put it in the deck, and then you go ahead and do the put, right? And then the get always looks to see if there's anything in the deck. So all that's encapsulated. We never have to worry about that. So rewinding back to where we were, we need those 4 states plus where our next character is coming from. Either it's coming from the buffered file or it's coming from the search string. So let's look a little bit at these specific tests. I think the way most people approach this is they write a little code and they run it through the tests, and it's not completely, but it's roughly in order of complexity, these tests. So if you try to get the first test working, and the second test, and the third test, I think that's going to be your best bet. Note that the first 3 tests are all working with file 1. So let me see, what can I do here? Let me do this. So this is as basic as the first three get. Replace the same size, replace where the replacement is smaller, and then replace where the replacement is larger. So you get those three working. The next three tests do the exact same thing, except our matches at the very beginning of the file. The next three tests after that, I don't need to look at it. I'm sure that it's going to be the exact same thing, except the match is at exactly the end of the file. So that's tests 1 through 9. And I guess we should let me go ahead and look and double. Oops. Here's the grading rubric. Let me see what this shows. Yeah. So for the first pass, you just have to pass those 9 tests based on those 3 files. And then all the rest are for the object-oriented solution. And so that Mississippi one, that falls in the object-oriented solution. We can look at the remaining. Let's see, what do we have? So 4, 5, and 6, that's the changing the ISSIP to POP, and all that's doing is it's putting this match at the beginning, end, and middle. Mississippi Delta would be when it's in the middle. So the wording's a bit chopped up to make it fit the beginning and end for 5 and 6. File 7, 8, and 9, I don't know what's... Whoops. Yeah, so this is beginning, middle, and end again. This one's a real pain because your search is 2 A's and a B. You have 2 A's and a failure, 2 A's and a failure, 2 A's and a failure. And how many failures do we have? Potential failure, potential failure. So the third time it matches. And then file 10 is pretty straightforward. This is just some miscellaneous etc password file. And what's it doing? It's finding the letter E. And wherever it finds the letter E, it's changing it to XYZ. So the idea here is just taking a general large file where the replacement's larger than the search and kind of checking the size of your deck afterwards. So that's the main purpose of that one. And that one shouldn't be, once you hit this point, then there shouldn't be any issues with that at all. This one, file 11, you replace X with XX, so this becomes 8 X's. This is where you get a little bit of fun with infinite loops. And then file 12. Three A's, X, Y, it fails. 3 A's, X, Y, and Z. So that's what it looks like when it's done. Yeah.
We need to take a look back at file 11. So it seems that 4x, we need 8.
Yes. It'll be 8 characters when you're done.
Well, it could possibly need to we need to check and see if we're replacing that 1x with the 2x's. The part that we've just replaced, we don't read it again.
Yeah, and this one ends up being an exercise in ensuring integrity of your where you think your get and put pointers are. If you've encapsulated things correctly in that buffered file, you get that done right first, this shouldn't be any problem at all. It should do this one fine. So, I'm at a point now where I don't have much more to share and I need you to ask me questions. So you've really got to go and bang away on this. You do not want to wait till this weekend to do this, I guarantee you. You need to spend between now and Wednesday coming up with some problems that we can talk about. Okay? Any other last minute questions or please? I'll take please. Huh?
Buffered file put.
Yes, buffered file put. What would you like me to talk about? Just in general?
Yeah. We have our set position, get positions. And they start out as 0, right? So we only set or increment them when we have matches or failed matches.
Buffered file has no concept of string substitution. Search, replace, none of that. Buffered file has no idea. Again, it's inheriting from fstream. So you'll note here in this bit of code, this was from a previous class, November 30th, that I copied over to today's notes. You initialize the base class with a provided file name and showing that it's going to deal with both input and output. You have a couple private variables representing your positions for your getter and your putter. That's all that is. Here's get. But you're asking about put. If set position is equal to get position, you're going to do some stuff. And then you're going to basically do these three. P put tell P, and this is put, and this is put. We'll copy paste, search and replace. So let's assume this isn't an issue, right? We can ignore that for the moment. Under normal everyday circumstances, you ask it to put a character. It seeks that stream position to wherever your put variable is, puts out the character, and then refreshes that variable to its new location. Again, you could, if you wanted to, you could just do and have the same effect. But for whatever reason, I like this, but go with whatever you like. All right. But here's the issue. If they're equal, then what do you need to do? Yeah.
Probably first get a character, put a point into the array, and then do the rest.
Maybe do these. don't put in.
Negotiate with overshadow the parameter.
Something like that. Yes.
Do we have to record, to get position, we have to record that we got a character from the get position. To move the get pointer on the internal get.
On
Because
this.
the outside world will expect that the get pointer is in the exact same place as it was with it or with it not.
The outside world isn't aware of it.
Isn't aware of where the get pointer is.
Correct. Right, buffered file is encapsulating all that. So you just tell buffered file you want a character, and it will give you the correct character. Now, here,
Where that character comes from and where it goes is not concerned with the outside world.
with regards to the file itself, your algorithm, your search and replace algorithm, does need to make a distinction where it's getting characters from. It's either getting it from buffered file or it's getting it from the search string. But that's a level of abstraction above this. This is closer to the physical file.
So at line 13, we're setting overflow equal to the get character.
Yes, a character is being read from the file and is being inserted into that character. And then on line 15, I go ahead and put that on the deck.
Under what circumstances do we need to get characters from the search string rather than from the file?
You have to get characters from the search string if you've had an unsuccessful search. Part of the definition of that is that your algorithm shouldn't care one way or another, but that only becomes relevant if your search string is greater than one character in length.
I understand the concept of getting characters from the search string. We're getting characters and we're comparing it to the search string to see if there's a match. It's a partial match. You would be getting characters from the search string.
You need to abstract this idea of. So we have this concept of get has two different levels of abstraction. The one we're looking at on the screen now is intimately associated with the file. Then there's a higher level abstraction, which means getting a character for the sake of the search and replace algorithm. And the getting a character for the sake of the search and replace algorithm is going to look for it it's either going to ask buffered file for it or it's going to get it from the search string. You could even, I suppose, if you want to try and be OO about it, you could put a class that wraps the two, right? Keeps the search string and keeps a buffered file, and then it looks back and forth, and then you just ask that one thing to get. But you would have to inform it of its state, whether there's a failed search or not. My recommendation is you get this buffered file working, and then you just start going through those tests, trying to get each one to work. That's going to be your best policy, probably. As I said, once you pull your hair out over this thing, then you have a really good idea of what the problem is, and now looking at an object-oriented approach from the beginning becomes a lot easier. Okay. All right, so I am going to stop this recording.